Okay, here's a whole screen full, but what we have here is a lens, and a single lens, and this lens suffers from spherical aberration. Here in this diagram you can see the OPD, and you can see that there is indeed fourth order spherical aberration. If you look at the sidles, then we see this is the spherical aberration term, about 0.3 of a wave spherical, and the other aberrations are 0. Okay, we know if there is spherical aberration that applying focus will increase the intensity in focus. This is the spot. The resolution is not that high, but you can see there is an area around where there is also light. Here you see the geometrical image of the spot, and in between I have drawn the airy disk, and you can see there is a whole ring of light here. And if you look at the cross section here through this spot, you can see that the intensity goes up to about 0.75, while 1 is the diffraction limit, is the perfect image. Well, here we have a true focus diagram, and now we are sitting here in this plane, and you can clearly see if I apply defocus, then my spot will decrease. That was also shown before. Okay, but now the question, where do we shift our image plane? To what position? And then it's very convenient to apply the Zernikes analysis, which is done here. This is a whole list of Zernikes terms. Maybe some of the people here are familiar with that. For the others, I can explain that the first terms with the 0, these are the symmetrical terms, and they are the lowest order, the defocus term, then the fourth order primary spherical term, the sixth order spherical, and so on. And the next group are the uneven asymmetrical terms. The lowest order is the A11, which is the tilt of the wavefront. Then the A31 is the primary coma. Then we have fifth order coma, and so on. And here we have the even unsymmetrical terms, and the most familiar here is the primary astigmatism, and we have fourth order and sixth order astigmatism. So you can...
Those higher orders, or fifth and seventh orders coma, they are not described by the sidles?
No, the sidles, they only...
Go to the primary.
They deal with the primaries, yes. Okay, what do we see from here? We see that there is a defocus term of about 85 milliwaves in RMS, and that corresponds with a defocus of minus 58 micron. Furthermore, we have a spherical aberration of about 22 milliwaves and a very small amount of sixth order, but we can neglect it. Okay, now we see when we shift our image plane 58 microns to the left, then we should be in best focus. That's what the Zernikes theory predicts. So in the next configuration, this is done. So we have moved now to that position, you can see from the OPD that they really are much smaller now. And if you look at the geometrical spot, it falls fully within the area diameter. And here we have more intensity. That's better shown here. We go all the way up to 1. You see, the lens was not so bad at all. And if we look at the sidle, obviously nothing has changed, because the sidle always is sitting and observing at the paraxial focus. But if we look at the Zernikes again, then we see that the defocus term is gone now. So we are sitting in the best focus. And the only thing that remains is the spherical aberration terms, which we have found before. You see, they are completely uncoupled. Right? So you can use the one for shifting and the other just stays the same. Only if you stay within the diffraction limited region. If you go to very large aberrations, that will no longer be the case. But for small aberrations, this is the case. Okay, now in the next example, I have added field here. And now if we look at our spot, this is again in paraxial focus. We see a defocus, and also we see asymmetry. If you look at the geometrical focus, we see a very large asymmetrical spot shape. If we scan through this spot from this is from the bottom to the top, so from south to north, we see a very weak intensity. And this is the OPD, and you see that there is, besides spherical aberrations, we also have other aberrations here. Okay, let's look at the sidles. They state that we have the same amount of spherical, which is obvious. It's the same lens. But now we've added coma, about comparable amount, also astigmatism, field curvature and distortion. So all the aberrations are here now. If we look now at this plot, we see that these are the tangential and sagittal focal planes. Okay? And we are now dealing at the edge of the field here. And this here is the image plane. And one can imagine that best focus is somewhere here. So now we not only have to deal with spherical aberration, but also with field curvature and astigmatism. So we have to shift our image plane to a different position now. But where? Okay, we do not learn that from the Zeidels. But if we apply a Zernikes analysis, it tells us that we have a much larger amount of defocus now because of the added field curvature and astigmatism. And we have to shift it about 172 microns to the left. And when we are there, we are sitting again with about 23 milliwaves of spherical. And also we have about 41 milliwaves of coma, slightly higher order coma, and about 93 milliwaves of astigmatism. And it also tells us that in order to go to maximum focus, we have to shift in the lateral direction over about 2.2 micron. Okay, now we apply the the shift along the axis. So in the next configuration we have shifted exactly over that 172 micron, and now we are according to the Zernikes theory in the best focus. And if you look at the geometrical focus, we see that the spot is much smaller, but it's still asymmetrical. There's nothing we can do about that. If you look at this diffraction spot, we see that it's really improved, but it's slightly shifted to below. And here we see a scan through this focus, and if we look at this position here, we see here at the top, we see indeed that we have to shift our area of interest about 2.2 micron to the left in order to reach maximum focus. So all that information is available when you do a Zernikes analysis. And when we apply the analysis again in this focus, we see that the defocus term is gone now, because we are sitting in best focus, and we still have that 2.2 micron because it's not possible to move our image plane north-south. That unfortunately cannot be done easily. And we're sitting with the same aberrations. They still have the same value as before. So you see that the Zernikes, they completely resolve the wavefront in orthogonal contributions.
It's also possible to do some extra curvature of the image with Zernikes.
Okay, the last example here is a wavefront with a pure sixth order aberrations. This is purely sixth order aberrations. And you can see that the spot is really large here compared to the airy disk. And if you look at the sidles, they don't give very much, only a very small amount of spherical, because the sidles cannot deal with sixth order spherical or sixth order aberrations in general. So now, applying the Zernikes, it tells us that we have defocus amounting to about 90 micron focal shift, and then we end up with about 56 primary spherical and about 10 sixth order spherical. And we end up with, here if you look at the RMS at image plane, at the current image plane, it's about 143, and at the best focus it's about 57. So it tells us how good this lens can become by shifting our focus. So that is done now, and you see here the improvement. It's clearly diffraction limited now. You can see it here as well. And if we apply Zernikes again, the defocus is gone and we have the same amount of spherical. And now we can see at image plane and at best focus they are equal. So this is really the advantage of working with Zernikes when you are working near the diffraction limit.